What's it doing now? A different screen. Share content. Weird. I'm just having trouble sharing the screen like normal. It's not giving me the normal look. Let's try this, but I don't know if that's right or not. So can you see the lesson 38 like normal on the screen?
Yeah, it's up.
It's like normal? Okay. It was definitely not looking the way it normally would look for me on my end, but weird. Okay. Things might have updated or changed or something, who knows? All right, so the videos from yesterday, people that were away for that math contest, you're able to see them?
Yep.
Yeah, perfect. Okay. All right, so you noticed, well, I did also email it out, but there's an assignment to do with that lesson. I originally had said in the lesson do Monday, but I had forgotten Monday is a holiday, so do Tuesday, so people have time to ask for a little bit of help on Tuesday, and of course today. So, all right. So we're going to go looking, or going to start looking at what's called a banked corner kind of question, starting out with no friction, and then I think I'm going to postpone the with friction to give us a chance to get to be good at the no friction case before we tackle the friction case. So I'll skip ahead to kind of the next thing to do with uniform circular motion so that we can tackle the banked corner question with a little bit of a time delay in between to get good at this stuff before we tackle the harder stuff. All right, so the stuff that we're looking at today is it's hard to visualize. So I've got a couple different ways that I'm gonna show you. Luckily, I have a video from something in room 124 that I've used in the past to help visualize it. But what we're trying to visualize is so you're traveling on like a banked corner, and if there's no friction, so I want you to visualize like a car traveling on a banked corner like this. Like it's like a highway. They have banked corners, but this is like extreme, right? So you're on like a racetrack, and so it's really, really obvious. The bank of the road is helping you turn that corner. It's helping provide that force towards the center in order to be able to have uniform circular motion, right? And so we're going to look at a special case where we're looking at if there's no friction. So picture it being a really, really slippery track, like freezing rain day, hoping you're going to coast around a banked corner on a highway, and the bank in the corner helps you actually turn, because certainly the traction is not going to help you turn because it's so slippery. All right, so if we're trying to think about forces and analyze this situation, what would be a great first step? Well, a great first step would, of course, be to draw a free body diagram. And so I have this thing set up so I can sort of drag the free body diagram in. So drag the white star to the yellow star. And that is the free body diagram we're looking at. Okay, the car has gravity on it, of course, and then it has a normal force on it that's perpendicular to the surface, perpendicular to the roadway. There's no other forces on it, right? Because that's just, there's no friction, there's nothing else going on. So we have an idea of the free body diagram for this, and of course it would like apply to this one too, right? But whatever. So we're picturing gravity and we're picturing a normal force. So the next thing to start to think about is how well, when we analyze this out, right? So the component of the normal force that's towards the center of the circle, right, is the only force that's in that direction if there's no friction. So picture the component of that normal force towards the center of the circular motion. I'm looking at this guy right here. So Fn x component, right, towards the center. That's the only thing that's towards the center if there's no friction. So that must be your centrifugal force, right? Because it's the only force that's towards the center. Basically, we know that Fc equals F net. Right, so FC equals F net, let's say it like that. And we know that in this case, the net force in that direction, if we're calling this the X direction, because that's the direction of the acceleration, right? We got AC in that direction, so the X direction is that direction. The only force we have, like if we're thinking of net forces adding up all this stuff, the only force we have in that direction is FNF, is the normal force component in that direction, right? There's no other forces. In this particular case, that is when there's no friction, right? If there was friction, of course, then you might have some sideways force on the tires, turn the corner, and so on. But we know in this case, this special case of no friction, that component of that normal force from the track that's pushing on a diagonal, there's a component sideways, and that's what's providing the circular motion. So there it is, right? There's that yellow version of it in this case, nice and visible. So, you know, what's this thing here? What force does it feel like is on the driver, and what is really on the driver? What we're thinking about, right? So the driver kind of feels like there's a centrifugal force pushing out, and then the car, the seatbelt, the person strapped into the car would be pushing inward, right? So picturing this here, that the driver's going to feel like there's a centrifugal force outward, right? And is going to feel that push that's balancing it inside the car. And so, of course, remember, this provides the zero acceleration relative to the car, right? So this is like F net equals 0, and I have to be careful here to be like relative to the car, right? So that's our non-inertial reference frame. So we definitely can think about that in that reference frame. And that's just to review what we looked at recently. Okay, but when we analyze this, we're going to look at the diagram more, the free body diagram, like this is the inertial reference frame diagram, right? This one here, the inertial reference frame. And you can think of that certainly as like what's really going on relative to Earth, right? But yeah, it's still logical inside the car to look at this, because experiments inside the car would have this force on it. So yeah, so to help visualize this, if you're not already visualizing it well, I have this ball and bowl in 124 that I've always show. Let me just get that running here. It's banked corner, Kingston, physics videos, banked corner. Banked corner, no friction. So this is what we're talking about. Give it a minute here. Okay. So what you're visualizing there, what you're seeing there, is uniform circular motion. From a banked corner, that ball is going around and around in a horizontal circle in uniform circular motion, and there isn't any friction that's holding it up. There's rolling friction, but that's just going to slow it down over time, right? If you didn't have it spinning sideways and I let go, obviously the ball is just going to roll right down to the bottom really quickly, right? So the normal force perpendicular to the track, to the bowl, has a component towards the center. So we have to draw it kind of like this and like this if we were looking three-dimensionally at this, right? Away from the bowl there, component towards the center, and it goes around and around as a result. So wherever I stop this thing, if I stop it over here, it's going to have a normal force out like that, a component of it towards the center. Okay, so that is what we're talking about. Inevitably, when I show this and talk about this, someone says, "Ooh, that's like the little funnel thing that the coins you see in the mall sometimes when we used to be able to go in malls." So this person posted a video of it. So you get the coins going down the funnel here. So you picture those as somewhat uniform circular motion, except of course friction causes them to slow down, so they spiral inwards. But at any rate, it's still somewhat uniform circular motion. Okay, so hopefully at this point, when we have no friction and so on, you can tell that there's like a specific speed, right? If I, especially in class when I do this in person, if I spin this thing faster, then it goes out to a bigger radius, it goes out higher. And as it spins slower, it goes down, just like in the coin one, right? That slower speed, once the friction takes over, they go to a smaller radius. And at the faster speed at the start, they're at a big radius, right? So there's definitely like a specific speed that is needed for uniform circular motion. And that's because there's a specific force available, a specific acceleration, actually, I should say available, but it's force paired up with the mass amount that you have, right? Because you're talking about the force that's causing all this gravity. And there's a component of that specific amount towards the center. So here we go. And analyze this thing. In the past, a long time ago, I started with this page and no one knew what I was talking about. So hopefully you know what I'm talking about now because you visualized like the car on the track, the ball on in the ramp surface. So here's the object, the car, the ball, and here's the banked corner, just like a little slice of it, right? That banked corner, I'm going to erase this in a second, but that banked corner would continue off like this, you know, and the ball is going around and around the circle. Okay, you just have to visualize that. So yeah, we've got horizontal uniform circular motion, UCM. So the centripetal acceleration is sideways, right? So that's probably, that's going to be what we're going to define as our x direction. Oh, that's a little crooked. But that's our x direction and our y direction. Basically, as soon as you see like an acceleration, you're like, ooh, let's call that the x direction. That's just good practice. And so we've got a small car on a highway on a ramp. What speed would the car need to be traveling to have uniform circular motion if there's no friction? So there's a specific speed. If it was going too fast, it would slide outwards. If it's going too slow, it'll slide down the hill, right? Given the mass, in this case, I think you'll see in the end that we don't need it. But sometimes it's easier just to work with mass as we go, right? So the driving starting point for this thing is that if we are in uniform circular motion, then we're staying in this horizontal circle. Like when you saw the ball zipping around and around, right? It's accelerating towards the middle. Horizontally, there's accelerations, but vertically, it's staying at that same height, especially this one. Not so much this one, not the coins, but this one, there's less friction, so it stays at the same horizontal, same vertical height as it's rotating that circle. So we know that acceleration in the y direction is 0. It stays in that same horizontal circle at the same height. But we know the net force in the y direction is 0. And if we look at our free body diagram, if I go back to even this one here, what this diagram isn't drawn quite correct, actually, which is fine. That's the way free body diagrams work. You draw them and then you analyze them and you go, wait a minute. I have something different. I need to modify it. So you'll see we can come back and modify this one in a little bit. But basically, I want you to be starting to look at this and say, okay, I know that in this diagram, we should have a net force in the y direction equal to 0, right? So we know we have the gravity force for sure. And so we know there must be a force that's balancing that. So I'm going to just kind of draw like this and say, okay, there must be a force upwards that's balancing that in this uniform circular motion. You with me? Right? So what force is providing that upwards force like that? Well, it's actually this normal force. And so the way this diagram was wrong, the way it was, is that this normal force actually has to be a lot bigger in order to be able to provide that upwards component. in order to be able to balance gravity. Okay, so you're going to see on a slide in a bit, I'm going to say, notice that the normal force is actually bigger than gravity in this case, because it's providing that acceleration towards the center, right? So the blue normal force that I've drawn there is actually bigger than gravity, right? That's like, you feel that force, you're getting like slammed into the car because of the corner you're going. Okay, so that's a little bit of a weird thing. So that's the correction that really should be on that. I don't know, free body diagrams, I want you to feel okay with just drawing forces and saying, okay, I get it, there's forces in these directions. The sizes come from further analysis. So I feel okay about that. So our analysis is, of course, here, like I said, that we've got the gravity force and the y component. There's no other forces. And so basically that shows us that the normal force, y component of the normal force has to be equal to gravity, right? That's algebraically what that's giving us. Could show that a little bit more if you wanted, but that I'm just subtracting FG from both sides. So let me just do that with purple or something. So subtract FG, and it literally gives us this equation. So that's showing that vertical arrow has to be the same as the other vertical arrow, right? And then the math for this, if this angle is a 20 degree for the ramp, then you can see that there'd be a 20 degree in here as well. That's just Z pattern. And then with this being a 90, you can tell that depends on how you want to analyze this, I suppose, but I think we're probably okay with it at this point, just saying, okay, that's the 20 degrees. So that's why I'm saying here that the y component is equal to Fn cos 20, right? We got the normal force, we got the component of it vertically, so we're looking at being adjacent to that 20 degrees, right? It's kind of easy to see that the 20 degrees is this one because it's a small angle. It's trickier if the ramp's at 45 degrees or 40 degrees. It's harder to tell because the angles are all about the same size. So that's actually a tip for you if you're having trouble seeing which angle's which. Just redraw it with smaller angles to make the difference between the angles more obvious. Difference in size of them. Anyways, so we know that this y component is the same as the gravity. That could just be written as mg, by the way, of course, right? So I'll come back to that later, but that's 9800 because we actually had a mass, but it could be just m times 9.8. So we're getting like an actual normal force rather than a normal force in terms of the mass. So it feels easier, more understandable. In general, that would have been, like I said, this would have been m times 9.8, right? Because the m was 1000. So in general, that would just be mg over cos theta. And that's okay. That would still represent the same thing. So the next step is, this is that note that I said I was going to point out. Note that in this case, it's kind of weird, right? That normal force is bigger than the gravity force. And that's because of the uniform circular motion. There's an acceleration, right? That's making the normal force be bigger. Okay, and that's providing that uniform acceleration, of course. So the component of it, that's our next step, okay, that we're leading to, is the x component, the sideways component of this normal force, is providing that force towards the center. So that's our next page to work on. Take a breather here, look at it, copy down what you got to do, and ask questions. Where are we at on this? Are you following me here?
I'm not really sure how we figured out that between Fn and Fny was the 20 degrees.
Yeah, it's a little weird, right? But think about Okay, so let me analyze it a little further. So this right here is 90. And so you could tell that this is like the other angle, right? So if this is make up to 90, that'd be 70. So we know 20 there. We know this 20 for sure because that was given. This 20 is by Z pattern. So it's kind of obvious. Then you could say, oh, well, by 90 degrees, this must be the 70. So then you could say, okay, well, then this is 70 because it's an opposite angle. And then you could say, oh, this is 20. And then like basically all of the angles just fall into place after that. And so then I guess at this point, once I label this one here as 70, then I could point out that that's a 90. And so this is 20 because it adds with 70.
Okay, there we go. That makes sense.
Yeah, so it's a bit of a leapfrog sequence of events here. You can also look at it as, let me use a line tool here. So this line here, right, being horizontal, when I bring that line, to 20 degrees, picture there being a corresponding line here where we would normally be perpendicular to that horizontal one. So we'd have a horizontal one like I had here a second ago. Oops, it's smart board or these computer screens messing with me a little bit. I think you're good with it anyways, but I just want to show a little bit more. So there's that line, and we normally have a 90 degree to it, right? And so picture as this one, as down here, rotates up to 20 degrees. So this would, if I group those together, like that. So I say, okay, rotate these to 20 degrees. See how that vertical also rotated 20 degrees? So that's another way to sort of visualize this. I'm just trying to give you multiple ways of thinking about it. So as this rotates 20 degrees, this rotated 20 degrees obviously as well. So that's even easier just to visualize, but certainly the parallel lines theorem and opposite line and then complementary kind of led to it as well. So the 20 degrees, okay, good.
Oh, sorry. Continue. I'll ask after. Sorry, I thought you were done.
I think I'm done.
Oh, okay. Sorry. So there's the FNY and then there's the FNX, but there's also like just a plain like FN. Like how come we have all three of them?
So remember that the actual forces, go back to the original diagram here, the actual forces that are on this car is the gravity force and the normal force. All we're doing is when we're showing FNX and FNY, we're just saying like the components of those things, right? So I guess sometimes we draw this on the diagram where it's like dotted. So like I have to go to a smaller white line here so I can do this better. Let's go smaller white line. That might be too small, but anyways, dot, 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 so like that's the X component, F and X. And then it's supposed to be an X. And then we have also the vertical component of it, right? F and Y. So those aren't actual like other forces. Those are just showing the components of the forces that we know are on it.
Okay, thank you.
That makes sense? Yeah. So it's not, we're not adding new forces. We're just showing the components. So we still just have the blue forces, the normal force and the gravity force, but we've got the component of it visualized as F and X and the component visualized as F and Y. So just to recap, we know this thing is not going up or down. It's staying in this uniform horizontal circular motion. And so vertically, we know that there's no acceleration. So we know that F and Y is 0. And then in the Y direction, we know that there's a gravity force and there's that component upwards. So we know that Fg plus Fny has to be 0, which tells us that Fny equals the opposite of gravity, which tells us it's 9,800 or mass times 9.8, right? So we know that's mass times 9.8, but we also know the geometric relationship between normal force and its component, right? That's always just the cosine if you're adjacent and sine if you're opposite. So since the green and Fny is side, it's adjacent to the Fn, we know the Y component equals Fn cos 20. So that gives us the normal force, the actual value, right? Because we know the mass, or it would be mass times 9.8 divided by cos theta, cos 20. So the next step is to say, okay, well then let's figure out that that X component, right? We know that X component's providing uniform circular motion. Let's talk about it. So the x component provides the force for circular motion. For it to be in uniform circular motion, obviously the only force on it in the x direction would be the centripetal, and there's only that normal force in the x direction, right? That's how I'm analyzing that this is true, right? Sometimes I'd show here too the idea of F net being, I still got my white pen I think here, this is like whatever forces are on it added up, right? Well, there's only this one. So the net force has to just be that x component of the normal force. So algebraically, we know that that's Fn sine 20. If we go back to the diagram, it's pretty easy to see, right? We're looking at being on the opposite side of the 20 degrees. So I could label in here, the Fnx as well. I don't know if that, that's your Fnx, right? On the opposite side of the triangle. But generally, math people and physics people get kind of comfortable with either visualizing the x component there or here, okay? And so it's easier there, of course, because you can see it's opposite of 20. But physics people tend to like it here because then it's actually showing, the force on the body, right? So Fn sine 20 is what that is. So that means we know the normal force values, mg or mg divided by cos theta, I should say. So that's the normal force that we figured out before, either as a number if we know the mass, or as mg over cos theta. So that means the centripetal force is equal to a value, right? It's 3,566.9, or it would be equal to, right? Or it would be equal to mg over cos theta times sine theta, which, if you wanted to simplify your life a little bit, especially in the old days when you had to look up numbers in a big table of values, you could just look up what tan theta is instead of having to look up the decimal values of sine theta and cos theta and then do a long division because calculators weren't invented yet. You just look up tan theta. I don't know if anybody's ever sort of shared that with you or not when you're doing the trig identity stuff in grade 11. Like, why? why do we do this? And it was actually it's really to simplify results. Scientists develop equations for things, and instead of leaving them in big, ugly, more complicated versions than they need to be, trig identities allow you to simplify it down to a simpler equation. So if you're going to give an equation for centripetal force, you'd be like, oh, it's mg tan theta, right? There's actually a reason for it. But. So, question? Okay, so that's the centripetal force. So got F net. This is what's supposed to be at the time like got milk, right? So like that commercial, So like if you have F net, then you can get acceleration, right? So let me just write that in there like that. If we know this is F net, right? So F net allows you to get acceleration, right? There it is, and there it is, F net and acceleration. So we're able to get the actual centripetal acceleration as well. There's like an acceleration of 3.5669. I'm keeping extra decimals all the way through. So this, in general case, notice that this, I said was mg tan theta, right? I have my in general over here as well still, but I'll just write it in. This is mg tan theta. So was the mass needed? You can tell mass really wasn't actually needed. It just kind of is easier to actually feels easier at least to have numbers as you go through things. So that's the sine theta over cos theta is tan theta thing. But yeah, so that would be, ends up being just g tan theta like I had up there. Okay. So acceleration, oh, what was our original question? Our original question was what speed do we need to go, right? What speed do we need to go for uniform circular motion? So maybe I should back up the truck a little bit here and remind ourselves. It's like if we get AC, right? We know AC equals v squared over r, and then it's like, oh, we got the r value, we've got the acceleration value, we're going to be able to get the speed. That was our main, process right from the get-go. So now that we have the centrifugal acceleration, it shouldn't be too much of a surprise to be able to say, okay, well, we've got, v squared over r, and so we can multiply it all out. Yeah. So notice it's like g tan theta. The mass doesn't matter, right? G tan theta is that 3.5669 ... keep lots of decimals, multiply by 80, take the square root. You've got the speed would be 16.89 meters per second. In general, it'd be like g tan theta times r, right? Root of it. Think of the algebra. Think of the algebra you would do for solving this. Multiply both sides by r, and then take square root. And that's exactly the kind of equation you might, find if you're looking up an equation for the ideal speed, or this is an equation for the ideal speed, right? So this is ideal speed for uniform circular motion with a banked corner, with an angle and a radius, right? And of course, it's on Earth, right? So this is a Earth calibrated result for ideal speed. So for any question from now on, if you wanted to, you could, it's kind of not the point of this, mind you, because the point of this is to be able to understand how to analyze circular motion. But engineers, right, don't do this kind of calculation every day. In fact, I don't know if they'd be able to be honest. They tend to look at results that physicists develop for them and be able to just use them, right? But at some point in their training, I'm sure they had to, see that the equation was true. Otherwise, you're just taking someone's word for it or whatever. But yeah, we could put in the radius of the circle. We could put the angle of the roadway and actually calculate out what the ideal speed would be. Or vice versa. You could plug in, I want people to be going the speed limit, which is 80. And I say, the radius of the roadway is based on the rock formations in the land. We're going to fix this number to be a value, in which case we can figure out what the best angle would be to make the roadway. So pretty neat application of what we're talking about. This is like the engineering design for roadways. Right? Make the angle nice, make the angle the ideal angle, and you drive around that corner and you don't feel like you're getting thrown outwards. You don't feel like you have to hold on for dear life and steer, and it just kind of just drive it very, very naturally and relaxed through the corner. So I hope you appreciate the idea of that, because that's pretty neat stuff. There's the questions to do with it for you to do. And they are ready to be posted as well. Just check. So many different things going on right now. I keep forgetting, did I do that one yet? But I'm pretty sure I did. Yeah, 38 homework answers, bank corner, no friction. Questions about banked corners with no friction? Just as a quick rundown again, just remember you're looking at saying, that the vertical forces are balanced, right? We're going to do that with the friction case too. The acceleration in the y direction is 0. But in the friction case, the friction, if there was friction here, for example, see how it's going to have a vertical component? So that's going to mess up this equation here. You're actually going to have FF in the y direction there. I'll just undo this because we don't have that on this page, but just so you can see what's going to come eventually. So when we get there, it won't be so hard. But our driving principle right from the start was that the acceleration in the y direction is 0, which allowed us to identify this y component value if we know the mass, or in other words, or theoretical value based on mass. We then used this value to be able to figure out the normal force, and then we used math to be able to figure out the component of the normal force, right? So the component idea led us to the vector and then to the the corresponding component. Alternatively, by the way, this might be neat for you to notice. We could, instead of using this value to get this value and then go to this value, right? We could have simply gone from this component to this component, right? And then you'd be using opposite and adjacent. Guess what ratio that is? You know the drill. That's tan, right? So the fact that tan ended up being in our equation is, in the end, looking at it, not a surprise. Okay, but that's the way I analyzed it gave us better footing in the uniform circular motion ideas. Because then we said, oh, that's the force for circular motion, and so here's the equation that's to do with it. So it's a little bit more of a complete physics analysis if I go through it the way I did. But hopefully it all makes sense in the end. Okay, so that is uniform circular motion, no friction, and we're going to look at some cases where basically weird results from circular motion, so unexpected results of circular motion and rotating frames of reference and so on. I have something called the Coriolis Effect, artificial gravity, real artificial gravity. I've already mentioned artificial gravity a little bit, just loosely. So now we can look at the details of it. We're going to actually work with cases where we're including the fictitious force in the free body diagram, and we're going to look at the effect that centrifugal force has on how you feel gravity, okay? The kind of forces you experience due to gravity, I should say, because you don't really feel gravity directly. So this should be review for us. We've already done this in good detail, but I'm going to show like the free body diagram for a person in a car turning a corner, and I want to look at the free body diagram based on the Earth reference frame, the inertial reference frame, and based on the non-inertial reference frame, based on using the car as your reference frame, right? So from the Earth reference frame, there has to be a force sideways to accelerate the person, because we know the person's accelerating in that circle, in the direction towards the center of the circle, right? So basically, you feel the seat belt, the seat, the door, whatever's pushing you towards the center of the circle. That's the force on you. In the non-inertial reference frame, you see yourself as not accelerating relative to the car, and so you should be able to analyze the balanced force situation in that, right? And so that is, where's my diagram here? I guess it's just, I don't have the circle drawn, but so then that would invoke, right? In order to not be accelerating relative to the car, you feel the car pushing on you, but you're not accelerating relative to it. So there must be a force that it's pushing against, right? There must be a centrifugal force in that non-inertial reference frame, right? So you have zero acceleration relative to the car, so you must have a net force of zero relative to the car, okay? So even though it's a fictitious force, it has a real effect in that non-inertial reference frame. So they're adding to zero, right? Yeah, so even here, actually, I shouldn't really say this because, the force felt, of course, you don't feel the centrifugal force. What you really feel is this, right? So this is actually written a little bit wrong, like that centrifugal force. Your brain tells you you're feeling it, right? Just like in gravity, your brain tells you that right now, because you feel a force on you, you're feeling gravity. No, you're actually feeling the normal force that's balancing gravity, okay? And we had that little discussion previously about how gravity, quote unquote, is not a real force. And so here, the centrifugal force clearly is not a real force, and it's experienced, it's felt sort of because of the non-inertial reference frame. Gravity is very similar to that, but not because of a non-inertial reference frame. Instead, it's because of your proximity to a large mass, which is warping space-time. And so you feel like you feel a gravity force on you because of your position in space-time. Weird stuff. So it's a similar analogy, and I definitely think we're onto something there in terms of like why gravity is hard to explain and mathematically mathematically too. If it's not a real force, it's actually due to space-time, then we should be talking about space-time in the description of it to try and figure it out. Anyways, so particles in a centrifuge, exact same stuff, right? Centrifuges are a circular machine, and you put something in it. You put a bucket of whatever liquid in there. They use the example always comes to mind is blood, because they separate out platelets and red blood cells and so on by spinning them around. But it's the exact same free body diagrams as in the car, right? Objects in a centrifuge really do collect along the outer edge, right? Which is why non-physicists think that physicists are weird when they say centrifugal force isn't real, right? Because it really does push things to the outer edge. But the way we're saying it, I think, is more understandable. Saying that it's real force in that non-inertial reference frame, absolutely it is. That's a review. Hopefully you're with me on that, getting to see it again and be like, oh, that makes more sense now. Whatever. Circular motion. Oh yeah, this one. This is physics in the world around you. Of course. Why would it be available still? Let's go to, it was called olive glass, including olive in glass. Probably only have one video entitled Olive, with olive in the title. There we go. So this is a Big Bang Theory episode where Leonard tries to impress Penny, I believe, with physics. I'm not sure if it went well or not.
So are the rest of you guys meeting this year?
Oh yeah, no. Oh. It turns out that Raj and Howard had to work, and Sheldon had a colonoscopy, and he hasn't quite bounced back yet.
Oof, my uncle just had a colonoscopy.
You're kidding. Then that's something we have in common.
Wow.
We both have people in our lives who want to nip intestinal polyps in the butt.
Excellent date conversation.
With the exception of string theory, not much has happened since the 1930s. You can't prove string theory. At best, you can say, hey, look, my idea has an internal logical consistency.
Well, I'm sure things will pick up.
What's new at the Cheesecake Factory?
I'm going to skip ahead a little bit. Eventually gets to the olive somewhere.
36 glorious summer.
After it.
Something cool?
There we go. Want something cool?
I can make this olive go into this glass without touching it.
How?
Physics.
Wow, centrifugal force.
Actually, it's centripetal force, which is an inward force generated by the glass acting on the olive. But if you were riding on the olive, you'd be in a non-inertial reference frame.
I don't know if you can hear it up. He's like, if you're on the olive, though, you'd be in a non-inertial reference frame, and so the centrifugal force would be,
Did you still catch up?
No.
Anyways, he's not okay. So, non-inertial reference frame. If you end up watching that episode later, you'd be like, oh my god, I understand that now. Ideally. So the question is about how Earth is a non-inertial reference frame. There's a bit of a video mention of this last lesson about how why don't we feel this kind of stuff? And the answer is actually we do. It's just pretty small effect, and so we can analyze exactly what that effect is. So if you're at the equator, you're in a non-inertial reference frame. You're traveling around the entire circumference of the Earth at the equator every day, right? So you're in uniform circular motion. So it is a non-inertial reference frame. So the in that free body diagram, you'd have a centrifugal force out and a gravity force in and a normal force out, right? So we don't normally list this centrifugal force in there, do we? But in reality, we're saying, yeah, it's a non-inertial reference frame. We should include it. So the gravity force, the normal force, and the centrifugal add to 0. right? This is like 0 relative to Earth, which is, in this case, a non-inertial reference. Same as saying, like, what's your free body diagram relative to the, what was this, like, relative to the car, right? So the car is accelerating, going through a corner. The Earth, essentially, is the surface of the Earth with you is accelerating, going around that corner. So in one day, of course, we travel the whole circumference, so we can calculate the speed, right? That's just a speed equals distance over time, circumference over time. So that looks like this. Not grade 12 physics stuff. This is just previous math stuff. Circumference 2 pi r from grade 9 or earlier. The time, in seconds. I take 1 day, multiply it by, 24 to get hours, and by 60 to get minutes, and by 60 again to get seconds, right? So we get a speed of 1,668.9 kilometers per hour you're traveling. If you're just standing still at the equator, you're actually traveling at almost 1,700 kilometers per hour. Kind of weird to think about that. Just on such a huge radius, of course, the effect is pretty small. It'd be hard to notice, but it's not something we can't measure. So we're going to calculate the centripetal acceleration that a person has at the equator due to this quite large velocity, just traveling around with the rotation of the Earth, right? So centripetal acceleration is easy. It's just e squared over r. So v squared over r, we got the v, we know the r, we can get the acceleration. The acceleration is, it ends up being, because the radius is so big, right, 0.033696. So that's a pretty small number, right, for acceleration. But if you express it as a percentage of 9.8, you're doing like 0.00033 divided by whatever, it's 0.34%. So the acceleration you're experiencing is 0.34% that of gravity. I suspect that might be bigger than you might have guessed. I think most average people might think like it's 0.000 something percent of gravity, because you don't tend to notice it, right? But it's actually a percentage of gravity that's measurable, 0.34%. So if we analyze this out in that non-inertial reference frame, we'd have a net force of 0, because we're not accelerating relative to the Earth. We'd have gravity, we've got centrifugal force, and we have the normal force. So we can solve out what we've got here. So normal force, what I do, I took away the normal force on both sides, trying to figure out what the normal force would actually be, right? So basically what you see here is your normal force certainly would normally be just gravity, right? But instead it's gravity reduced by that 0.34%, right? In the diagram that I drew earlier, we had gravity towards the center and centrifugal force the other way. And so it's going in as the opposite sign. Okay. I guess if I went back to this too, we're going to define this as the x direction, because that's the direction of the acceleration, right? So that's why the centrifugal force is going in as a minus. It's going the other way. So that gives us this. We got the m times the 9.8, or yeah, to take away that number. Instead of feeling a force on you balancing gravity that it normally would be, it would be 0.34% less, right? So I did include this idea of like gravity felt, because of course you don't really feel gravity, you actually feel the force that's opposing gravity, right? Which is really what we call our weight. So at the equator, just standing on a scale, you'd be 0.34% lighter. So, if it normally, what do we got? 1 take away 0.34, right? Well, anyways, yeah, you'd be 0.34% lighter. So 1 take away 0.0034, and you'd have your percentage of what you would actually weigh. So if you normally weigh 170, you would weigh, oh, I did the numbers wrong there. 100 take away 0.34 times 170 divided by 100. You'd weigh 169.42. Right? Almost like a half a pound, I guess that would be in that numbers. You know, it's yeah, suppose it could be measurable. Now, your weight fluctuates probably by a couple pounds per day anyways, really, right? So is it noticeable? Probably not. But I think it's neat that we can calculate it. It's actually 0.34%. Now, at the equator, of course, at the equator, you have this fast velocity, right? You've got this rotational velocity. If we were instead standing at the North Pole, there'd be none of that, right? So you'd have your full gravity at the North Pole. Now, truth be known here, the Earth is a little bit bulged, and so at the equator, you're further out, so it's actually an even bigger effect. You're even lighter at the equator because you're further away from the center of the mass. So there's other factors as well, but the centripetal acceleration needed for uniform circular motion and so on, and the resulting centrifugal force is actually a calculatable value. Other effects for this. So the artificial gravity idea, this video sort of shows what artificial gravity looks like and how you would do it. So wait for this ad from Special K here.
Special K helps give you the nutrients you need, made with whole grains, fiber, and real ingredients. For when you're ready to prove it. Special K.
So it's clips from the movie A Space Odyssey. And so there's some wording in this I don't like, but basically he's in this very obvious circular room. The circular room is rotating, and as a result, he's able to like run around and feel like normal gravity. Somewhat, anyways, feel like normal gravity. So I'm kind of surprised they haven't done this yet in like the space station and things like that. Instead of people being in space for a couple months or whatever they're there for, and then they come back and they have to rehabilitate because their muscles have lost so much mass because they don't work out. It's hard to. What do they have here? There's one video I had where they showed how you would, yeah. So if you're at the center, you'd be in weightlessness. And as you walk down that ladder, gravity amount gets more and more because you're at a bigger radius. So like up in the center, you're in normal weightlessness, just spinning without even knowing it. Really neat. It really would actually work. So the idea of it spins so you're thrown out, really, your body's just trying to go with uniform motion. But in a non-inertial reference frame, that's absolutely what it would feel like. So analyzing circular motion for artificial gravity. View full screen, peak width. So blurry for some reason. Okay, so what speed would we need to be traveling at with uniform circular motion if we had a radius of 400 meters, right? So if we tried to actually build an artificial gravity space station, what values would we have to have? I don't know why they're all blurry on us. There we go. So you have 400 meter radius, and we want to have the same acceleration due to gravity on Earth. Okay, if we had the centripetal acceleration be the same as 9.8, that would make you standing on the floor of the space station feel exactly the same as on Earth. So you could probably get away with making it be 75% of it or something like that, just so it's enough that it keeps you working out, but maybe not so hard to spin so fast. But the idea is you'd have this ring-shaped space station, and everything's blurry on this one, and you'd be rotating, and so you'd have a centripetal acceleration towards the center, just like you feel like you have right now up due to gravity. All right. So the math of this, we know centripetal acceleration, we want it to be 9.8. We know that the formula is v squared over r, right? So the v squared over r would equal 9.8. We said we wanted to have a radius of 400. So, I hope you're seeing that this isn't as complicated as it might have seemed looking at the introductory question on the page. You know, up here saying like, what speed would you have to have? It seems like, oh, that's crazy. How would you figure that out? What am I, an astronaut? You know, but it's not as hard as you'd think. The centrifugal acceleration is v squared over r. We want to be 9.8. So just solve for what the speed would be. So it turns out that you'd have to be going like 225 kilometers per hour with that size of a space station and so on. So, you know, perhaps that's too fast to be realistic. You know, you could, you know, maybe go with a smaller acceleration amount. Maybe that would be good enough. Or you go with a smaller radius. This radius was quite small in this picture. So that's fairly realistic. They didn't use a 400 meter radius. This 400 meter one would be like a ring space station that would be quite large. You'd have like tons of room for laboratories. This clearly was much, much less. Maybe like 40 meters instead of 400 meters, in which case the rotational spin wouldn't have to be as fast, right? But, you know, remember there would be this center that would be rotating with it, and it wouldn't matter. You'd be in there weightless floating around. As you climb down a ladder to this spinning station, gravity would just get stronger and stronger. The artificial gravity would just get stronger and stronger as you climb down the ladder. There was a video somewhere I had about that. It was really good. I think it might be from, I want to say, what's the other really good movie? It's not Gravity, I don't think. Anyway, so that'll come to me. Questions at this point? So artificial gravity makes sense. Very understandable. We can calculate numbers even to do with it. I.e., you can do that on assignments, tests, quizzes, whatever. All right. So other effects. Let's go with Coriolis Force. Let's do that. See if my links work fast here. To give my computer a break.
To an observer above the merry-go-round, the path of the ball appears straight.
So I'll start
While
this again in a
someone
bit.
sitting on it, the ball appears to curve to the left.
So this is again, we're just basically trying to look at unexpected results. So this is a merry-go-round, four people sitting here trying to roll a ball around. Watch the motion of the ball.
To an observer above the merry-go-round, the path of the ball appears straight, while to someone sitting on it.
And even we'd have to remember that video from 1960 where they drew a line. You'd have to like draw the line. This person throws the ball and goes like this. But then as it's hard to envision how that works. Like it actually looks like it curves and goes to here, but in reality it kind of just went like that. You'd have to draw the lines to see that it's straight.
While someone sitting on it, the ball appears to curve to the left.
So certainly here, though, from the non-inertial reference frame point of view, we've got a huge curve.
This exemplifies the Coriolis force, whereby to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
So these curved paths that you're seeing and would see if you're on a merry-go-round or whatever you call that thing, these curved paths are what's referred to as the Coriolis effect. So I'll play the Coriolis effect video as well. So I'll try and make sense of the Coriolis effect.
Is HelloFresh worth the press? Absolutely. In the beginning, I was doubtful too. Till I realized
2 ads. YouTube's greedy. Let's go Coriolis. Too greedy. All right, so Coriolis 211. That's the one that I wanted.
Coriolis effect. An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by 2 people on a merry-go-round.
So there's that merry-go-round analyzed a little bit for us.
That spins like the Earth, but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher. Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve.
So the ball gets tossed at this angle and goes out to here, goes straight out, right? From this person's point of view, the red person here, the blue person threw it at them, but as they watch it go, it curves off to the right, right? It curves off from their point of view to the left, I guess, but from our point of view to the right. Okay, so they're going to see this curved path. So I'm hoping this little analysis helps you understand why the ball was curving the way it does in the previous video.
From the vantage point of the catcher, the ball appears to curve away.
I don't like the way they showed the ball go there. It should have just been like going straight out, right? And he just rotates as well.
The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way.
So what's going to happen in this case is this person throws a ball towards the middle. They're going to try to throw the ball to the middle, right? But it has a big velocity sideways, and so it's going to curve off.
Is moving.
At the side, you have velocity. Here you don't, right? That's the difference.
The ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels farther. In the southern hemisphere,
if you threw it slow enough, it would actually loop and come right back to you because you'd end up going around to where you were, right? Or around to this side, I guess I should say. It's weird.
Sphere, rotation is clockwise when viewed from over the pole. Again, the ball follows a straight course, but its apparent flight path is diverted. This time, the effect is to divert the motion to the left.
Okay, so it's doing a good job showing that straight line, but in the curving non-inertial reference frame, right? It looks like a curve.
On Earth, all free-moving objects, including masses of air, are subject to the Coriolis effect. In the northern hemisphere, objects are diverted to the right.
So as air goes from the equator north, I have another page dedicated to this, but this air has velocity to the right because the Earth is spinning this way. Okay, so it has lots of velocity, like 1,700 kilometers per hour, right? Eventually, if that air just went vertically up to the North Pole, it would have a velocity of 1,700 kilometers per hour to the right relative to the North Pole, if it could get that far. But what happens is, as it goes, of course, there's friction and everything else, and interactions with other air masses, but it certainly does end up with a noticeable velocity to the right. That is what is causing the prevailing west winds in Canada. If you look at all pine trees, they all, swoop to the east from that wind that's coming from the west. That's the prevailing west winds in our weather patterns are because of this physics effect, the Coriolis effect. So I'll explain that again in multiple pages.
Direction of original movement.
Reverse is true from the other way. No velocity at all. So if you throw something straight towards the equator hard enough, eventually that velocity you don't have shows up in comparison to the velocity the Earth has. The Earth rotates out from underneath it, making it look like it's curving the opposite way. I want to analyze that one. That was weird.
In the southern hemisphere, the deflection is to the left.
So that's your first video to do with the Coriolis effect, to do with weather. Centrifugal physics. I forget what that one is. Centrifugal physics experiment. Centrifugal physics experiment. Love the soundtrack. observe a ball going across merry-go-round with various reference frames. Oh, they're going to keep rotating it so it's at the same angle all the time. They get their constant speed from that. Could mute this. I don't know if that mutes it for you though or not. That mute it for you. Music's annoying. They're not saying anything anyways. So they're getting it spinning, and then they're playing around. So if you ever have a chance to do this, you know what you're trying to do. So the person tries to throw it towards the other person, and it's like curves off to the side because of the Coriolis effect. If they're not just sitting and trying to roll it, it'd be a lot easier. So from the point of view of the other person, you're going to see them throw it towards, and it's going to go veering off. There you go. So if that person tries to throw at the person across from them, it might go to the person beside them instead, I think is what they're trying to go for there. Anyways, so that's just another video of the same kind of thing there. Merry-go-round physics test. Merry-go-round. I end up with redundant videos here, but merry-go-round physics test. Probably the same kind of thing. Yeah, it's like a product produced by students at one point where they're showing you can throw the ball back and forth, no problem. But when you're spinning, try and throw it and it goes off to the side. So they're probably explaining things here. I'm not sure. Oh no, it's just music. Anyways, their links are there for that if you want to check those out later in more detail. This was talked about in that previous video from 1960 as well. So just a little bit of a further analysis of this Coriolis effect. Gaspard Gustav de Coriolis or whatever, back in the 1800s, noticed the Coriolis effect. Actually, that was supposed to be last. So this object we know has like almost 1,700 kilometers per hour sideways. If you have an object here, if you just kick it, right, try and kick it all the way to the North Pole, what happens is that sideways velocity becomes apparent, right? It's moving sideways, but the Earth underneath it is moving slower and slower sideways. So objects here don't have as much sideways velocity. Objects here at the North Pole have no sideways velocity, right? So if you manage to kick a soccer ball all the way to the North Pole, it would literally, if there wasn't any air resistance and stuff going on, it would have a velocity relative to the North Pole of that huge amount, right? So it's going to keep that velocity, of course, because of inertia, and so it's going to show up, right? So it would travel this curved path, and that is exactly what air masses do. As air masses expand out and move, they don't have wings or whatever to steer and try and go in a straight line. They end up keeping that sideways velocity, and air masses travel towards the east as a result. So we did a lot of analysis in a physics class in university where we talked about this Gustav gun or whatever it was called, and this cannon could launch a projectile so far that they actually had to include the Coriolis effect in their calculations in order to be able to aim the thing, because it launched so far. If you're aiming north or south, it went so far that the Coriolis effect became noticeable. So they had to include that calculation into their work for aiming the thing. Kind of neat. So in this little applet, the red line is going to show the curved path relative to that non-inertial reference frame. The blue line is going to show what it's really traveling, right? So we got an object launched directly south from the North Pole. So directly south. from the North Pole, right? So it's going directly south, right? But at the same time, the Earth curves out from underneath it, making it appear to go towards the west. So the red line, that curving towards the west, is the path that it would appear to go. And so that strange sideways movement, that's a note for when people are doing this course independently, that weird sideways movement is explained by the ideas of the Coriolis Effect. So this one is an object launched directly south from somewhere around, so basically you're launching it, and again, it's curving, but I don't feel like we have to analyze it too much. Common myth. A common myth about the toilet bowl. So let's type in Coriolis again here. Coriolis myth.
Hey, Australian people, have you ever been to the Northern Hemisphere? Have you ever noticed whether your toilet drains differently than it does here? No? You heard maybe it has something to do with the Coriolis Effect? Welcome to another edition of I Don't Think It Means What You Think It Means.
So it's a common myth in the world that toilet bowls in the United States, or in the Northern Hemisphere, United States, because that's the center of the universe, rotate clockwise or counterclockwise, whichever direction it is, be clockwise actually, because if you think of the arrow, the yellow arrow going to the northern, to north, it was curving around clockwise, and then in the southern hemisphere it's the opposite way, for the same explanation. So a lot of people think that in Australia toilet bowls swirl the other way than they do in North America. So this is his discussion about it.
You probably don't spend a lot of time thinking about how water drains from your toilet, but somehow the idea that water drains differently in northern and southern hemispheres has made its way into our collective consciousness. Furthermore, the reason for this phenomenon has been pinned to the Coriolis Effect, which refers to the way the Earth's constant eastward rotation influences how we view the trajectory of certain moving objects. Because the diameter of the Earth at the equator at 40,076 kilometers is so much greater than it is at the poles at 0 kilometers, the land of the equator is moving lots faster than the land everywhere else, about 1,638 kilometers per hour at the equator compared to about half that at 60 degrees north latitude and pretty much stationary at the poles. And yes, the Coriolis Effect, named for 19th century mathematician Gustav Coriolis, does indeed influence objects traveling across the face of the Earth due to this constant eastward rotation. If you tried to throw a baseball from the equator up to your friend standing at the North Pole, your ball would appear to veer to the right because it would maintain the greater momentum of the place it started from. On the other hand, if you were throwing the ball...
It said greater momentum. He didn't have to use the fancy word momentum. He could have just said greater velocity because of inertia, right? So he really likes to use the word momentum, but we haven't talked about it yet, so soon we will.
To the South Pole from the equator, the ball would appear to veer to the left for the same reason. So although the Coriolis Effect is totally a thing, the application of this principle to draining water in Earth's two hemispheres is just bunk. Our planet spinning around once every 24 hours isn't a big enough deal to affect a toilet that takes 5 seconds to flush. Basically, the direction water drains is dictated by the shape of the basin.
And he says it's by the shape of the basin. I would say there's engineering in the toilet itself. The water shoots in from above on an angle to make it spin a certain way to help facilitate the flush down the toilet. Any bowl of water with a hole in the bottom, any sink you're ever draining, basically if the water in the sink had a little bit of a counterclockwise motion, that's the way it's going to swirl. If it had a little bit of a clockwise motion, that's the way it's going to swirl. You could experiment in the kitchen sink. If you have a double kitchen sink, fill up both and just gently swirl one of them a little bit clockwise and gently swirl one of them a little bit counterclockwise, and then pull the plugs, and you'll see that the swirl will end up being the way that the water was swirling a little bit. In toilets, like I said, there's a bit of a jetting where the water shoots in and kind of forces it to go a certain direction every time. But in sinks, it would just be kind of random depending on the last dish you took out when you're washing the dishes, whichever way the water happens to be swirling a little bit. The Coriolis effect, he's talking about planets, and you're moving hundreds or thousands of kilometers, and then the velocity you have at the equator in comparison to the velocity you have relative to the Earth as a result becomes noticeable. Is water moving thousands of kilometers in a toilet? No. So it's not going to have an effect. Is what I think, I believe. Let's put it that way. I'll show you another video in a minute. But yeah, water's not moving very far in the toilet, so certainly the Coriolis effect doesn't really have much of a chance to have a major effect. He talked about it because it flushes so fast. Yeah, I guess, but it's a really small distance also, right? There's also a myth out there that when they were drop form mold, like making the concrete molds for the CN Tower, that they had to account for the Coriolis effect, or else the CN Tower would have ended up being a corkscrew. Also completely false, because the concrete is not traveling thousands of kilometers from the equator towards the north to end up having a curve, right? So, it's just people get these ideas and they extend them in the wrong ways and so on. And it makes it hard to know what to believe, especially once I show you this next video. But let's see what else he says.
From the poles, which are naturally high pressure areas, to the equator.
So this is about air molecules.
Very many and unpleasant things that would be different. One of them would be that winds wouldn't blow either west or east.
So if we didn't have a rotation on the Earth.
From the poles, which are naturally high pressure areas, to the equator.
That's because of heat, by the way. Lots of sun exposure at the equator, expands out air, high pressure pushes outwards towards the north and the south poles. And then, of course, they curve and become the prevailing winds. He's saying, well, we wouldn't have that. They would just be going directly north and directly south.
There's low pressure and back again. But the Coriolis effect deflects these winds to the right in the northern hemisphere, to the left in the southern hemisphere, which creates weather systems that rotate clockwise in the northern hemisphere and counterclockwise in the south. Coriolis effect working at that scale does affect entire climate patterns, but it can't make itself felt on whatever you left in your toilet. Sorry. It's the Coriolis effect. Weather, not toilets. Got it? Good. Thank you for watching this episode of I Don't Think It Means What You Think It Means. If you have any questions... So
the idea that he's going by there, he didn't say it specifically, but toilet water doesn't travel from the equator all the way to the northern hemisphere, so it doesn't have 1,700 kilometers of velocity, right? Then I see this video. When I'm searching for a different video, what this video is searching for, I'll just show you briefly here. Spiral, that's not the one. Let's see if I still have it going here or not. Let's just do water from. So basically, if you ever go to a place where you're at the equator, there will be people at the equator, where the tourists are all gathered and everything else. They'll be showing people that water spins one way on one side of the equator and the other way on the other side of the equator. I don't know if you can hear me right now with this Ford ad going on. Holy. So basically, they'll have this dish and they show you, oh, the water spins one way here and it spins another way there. The one video that I really want to show, I can't find right now, but basically they have a dish over here on one side of the equator, and they basically make sure it has the water has a little bit of a spin the way they want it to go, right? Then they carry it over to this side of the equator, and as they do, they turn around subtly. Like they pick up the dish from this way, they come over here, and they turn around and they set the dish down. Well, then that turning around makes the water have a rotation this way, whereas here it had a rotation this way because they came over here and sat it down this way. Then they bring it over here and sit it down this way. And so the water's spiraling in different directions on either side of the equator. Clearly not a Coriolis effect. It's just a trick to get tourists interested, and the whole crowd gathers, and then next a bunch of coins are dropped in a hat, right? So there's videos of lots of this where they show like the flower spinning as it drains on this side of the hemisphere, equator, and the other way. Some of the videos you watch, though, they're more convincing than others. This guy, I believe, is the one that puts in a little cardboard to try and stop the movement of the
Spinning the
somewhere.
way that it
Anyways,
is.
it puts cardboard in to stop the rotation, to try and convince people that he's not tricking you. So this video, though, I stumbled across today. And I'm surprised at the result because I trust this guy. He's a former NASA engineer.
The far side is moving
He
too
doesn't try to
fast
trick people.
relative
He's a scientist and he explains things well. He's actually the same guy that did the gravity is not a real force. So let's watch this.
A couple of years ago, my friend Destin and I wanted to definitively answer the question, does water actually swirl the opposite direction down the drain in the other hemisphere? At the time, I was living in Sydney, Australia, and Destin was in Huntsville, Alabama. Those are about the same latitude, just opposite sides of the equator. So we created 2 videos that were meant to be watched simultaneously, and if you want to synchronize them yourself, you can click the link in the description. But we also recognized that that was a hassle for some people, particularly watching on mobile devices, and that's why I'm now releasing this extra wide video of both videos synchronized. The Simpsons did a whole episode based on toilets flushing the opposite direction in Australia. Plus, other shows have supposedly demonstrated this effect. So I've seen documentaries that seem to indicate that which hemisphere you're in determines which way the water is going to swirl. But there's this other group of people, and they seem really confident that it doesn't matter where you're at, the water's going to swirl however it wants. So is this a real effect or not?
The application of this principle to draining water in
familiar?
Earth's 2 hemispheres is just bunk.
But if you ever just look for yourself and
So
figure
you've got a group of people that say, that's ridiculous. The water's not traveling thousands of kilometers. How could it possibly have an effect? Right? And then they're testing it to see, because there's the 2 groups of people that say it does and people say it doesn't. So they're trying to be objective here and just test and see what happens.
which way your toilet swirls.
And spoiler alert, I'm
If you try it
surprised by
yourself,
their
you'll
conclusion.
find inconsistent results.
Here in Alabama, I've noticed that some
So there's the kitchen sink thing. If you give this one a little swirl this way and a little swirl that way, they'll definitely swirl those ways. By random chance, he's saying sometimes they swirl one way, sometimes they swirl the other way.
turn counterclockwise and some go clockwise.
This sink sometimes drains one way and sometimes the other way.
You see, most toilets have little jets in it, so the swirl direction is determined by the design of the toilet and not which hemisphere you're in.
In any container of water, there's always going to be some rotation. The water is not perfectly still. And it is this, rather than the hemisphere, that determines which way the water will swirl down the drain.
So it's a myth. Crossing the equator does not mean the toilet's going to change directions. But what if we come into the garage
Or
and
is
do a
it?
more controlled experiment? But what if we could eliminate all motion from the water? This is a 1.5 meter kiddie pool.
I have here a 5-foot wide kiddie pool.
Instead of filling the pool with no vorticity at all, I'm going against the way it's supposed to drain. So I'm trying to fill it with the flow going clockwise.
I actually fill the pool in the anti-clockwise direction to be sure that any clockwise motion we see is not due to the way I filled the pool.
So let's let the water settle for a complete day so that we know what this is.
I've left this water sitting here for 24 hours, so it seems like I've damped all of the motions from the filling.
Well, I'm not going to reach in and pull a plug out because that would induce some vorticity. I'm going to use this valve that I have connected to the bottom of the pool.
I really hope this works. Destin, wish me luck.
Good luck, Derek.
I'm about to pull the plug.
Okay, opening the valve in 3, 2, 1. Water should be flowing.
And the pool is draining. But you can't see any motion of the water just yet.
Okay, water's been flowing for a couple of minutes and I haven't seen anything yet, so we're going to put some dye in it.
To help us see where the water is flowing, I'm going to put some food coloring in on the 4 cardinal directions around the pool.
Check it out, it's like a tornado. Right off the bat, we got a counterclockwise rotation. We filled it up clockwise, and now it's going counterclockwise.
You can clearly see that the water is flowing clockwise in this direction, and that makes sense because that's how it should flow in the southern hemisphere due to the Earth's rotation.
We have a kiddie pool in my garage, and the whole Earth is rotating, and the water is going counterclockwise because I'm in the northern hemisphere. It's real. This is real.
So apparently, according to this, as the water moves from the outer edge to the inner, like the actual velocity difference from that, what is it, 4 feet or something, actually can have an effect, apparently.
Clockwise because I'm in the northern hemisphere. It's real. This is real.
But you can see what a tiny little effect it is and what extraordinary lengths I had to go to see this effect. So really, you're not going to see it in a bathtub, and you're not going to see it in a sink or in a toilet, because there are other sources of angular momentum that totally...
So that's the part here where my answer is like, is it a myth? And be like, well, yes and no. It actually can have, it is a real effect, but is it what's causing the draining in sinks and toilets and so on a consistent basis? No. But it surprises me that it actually has an effect even on this small of a scale.
Wash out this effect.
We just proved it because we just eliminated variables.
The Coriolis Effect is real. There you have it. It works. To understand how it works, imagine a pool with one edge touching the South Pole.
Think about a pool near the North Pole.
The pool is stationary relative to Earth, but every day it's actually completing one full revolution.
The Earth is spinning on its axis, so the pool spins around the pole once a day.
Now you can see the side of the pool furthest from the pole travels much farther every day than the side right next to the pole.
The whole pool is moving, but the part that's closest to the equator has more momentum, and the part that's closest to the pole has...
So as this part gets closer to the center as it drains, its rotation is going to become obvious. Its sideways velocity is going to cause rotation, I should say. It would be noticeable.
So the outer side of the pool is moving fastest towards the east, and as you get closer to the pole, the velocity decreases down to zero.
And the opposite analysis in the other hemisphere.
Relative to the drain in the middle.
Now imagine we drain the pool.
When we pull the plug, all the water starts moving towards the middle.
Water from the far side is moving too fast relative to the drain, and so it gets out ahead, whereas water from near the pole is going too slow, and so it lags behind.
The side nearest the equator is going faster, so that water outruns the drain. But the water nearest the pole is going slower, so it falls behind. So when the water approaches the drain, it swirls counterclockwise. This is the reason hurricanes swirl counterclockwise in the northern hemisphere.
So this is for, and no one disagrees about this, right? The swirling of hurricanes, they call them hurricanes and cyclones. They call them different things because they swirl different directions. But like no one just argues about that. But I think a lot of scientists would be surprised that it actually does affect something as small as a kiddie pool.
And cyclones swirl clockwise in the southern hemisphere.
The center of the hurricane has lower pressure, just like a drain.
So I think
I have the
that's
storm.
about it.
And that's the truth about toilet swirl.
There you go.
Hey, I hope you enjoyed that, and thanks for watching.
I sure did, because I learned something today. I would have said no. I would have said it doesn't have an effect. This little applet doesn't work anymore because Java is dead. But what I used to be able to show was that we have this ring world. This is an artificial gravity world. And so the question at the top here, as a final thing here, is artificial gravity. Would it be just like home? And the answer is sort of, but not quite. Okay, and it's because of this Coriolis effect issue. So here you have a big velocity sideways. Here in this situation, you'd have a little bit of a velocity sideways, and naturally based on the rotations. And here you'd have smaller and smaller velocities, right? So if you jumped straight up, right? If you jump straight up, then relative to that surroundings, the buildings, the poles, the wires that are supporting things or whatever, you'd actually have a velocity sideways relative to them. You'd have this bigger velocity still, this whole big velocity. Relative to the stuff around you would have a little velocity. So if you jump up and down, back in this video we saw, wherever it was here, right? In this scenario, if this person just jumped up and down, every time they jumped, they'd land a little further ahead than where they jumped because of their velocity sideways. Yeah, so you actually kind of jump up and down. You'd end up bunny hopping forward as a result. And this little applet showed that it had a spin, and you could launch a ball straight up, and it would literally go up and then land, and then up and then land, and then up and then land. So it would be similar to, very, very similar to gravity, except if you're tossing a ball up in the air, you'd actually have to put your hand ahead to catch it, right? So it'd be similar in terms of having to lift things against gravity, and in that case, against the centrifugal force. Both not actually real forces. Yeah, but when you toss it up and down, the difference would, so you'd be able to tell. If you were in a rotating reference frame for artificial gravity, you'd be able to tell because you'd toss something up and down and it would move sideways. You'd be like, oh, I must be in an artificial gravity situation. So that is it for me. I don't have these ones. I don't think I have those ones done yet, but I'll see if I can either post it or we'll look at stuff in help sessions once you've tried it and you feel you need help. Okay, so if I end up getting it posted, great. If not, we'll help you out in help sessions. Any questions right now? Yes.